It's a really great pleasure and honor to introduce today's speaker, Professor Sharbil Farhat. Professor Farhat is no stranger to AUB. He's visited us a number of times in the past. Professor Farhat is the Vivian Church Hoff Professor of Aircraft Structures, and he's the chairman of the departments of Astronautics and Aeronautics at Stanford, and the director of a Stanford CACS Center for Excellence for Aeronautics and Astronautics. Professor Farhat's interests are in computational engineering sciences generally, particularly design of complex systems in aerospace, mechanical, and naval engineering. He's a member of the National Academy in the US, a member of the Royal Academy of Engineering in the UK, and a member of our own Lebanese Academy of Sciences. He has an honorary doctorate from École Centrale de Nantes and from L'École Normale Supérieure Paris-Calais. He's a ISI highly cited author. This should be no stranger to you. Probably most of you have read his work. He's a fellow of many professional societies, SIAM, the US Computational Mechanics, AIAA, and the International Association of Computational Mechanics, and many others. He has had 90 PhD students and postdoctoral students that he has mentored over the years. And his work on aeroelasticity, CFD, dynamic data-driven systems, high-performance computing, model reduction has received, for that work, he's received many professional distinctions, including, I just can name a few in the interest of time, Lifetime Achievement Award from ASME, the Gordon Bell and the Sidney Fernbach Award from IEEE, the Gauss-Newton Medal from the International Association of Computational Mechanics, the Grand Prize from the Japan Society for Computational Engineering Science, and of course the von Neumann Medal from the US Association for Computational Mechanics. He was also knighted in France in the Order of the Academic Palms, and awarded, of course, the Medal of Chevalier dans l'Ordre des Palmes Académiques. Today, Professor Farhat is going to talk to us about real-time and data-driven modeling and learning for digital twins. Talking about learning, I cannot help but talk about the Turing Award today, the 2019 Turing Award, which is awarded to Jeff Hinton and Jan LeCun for their work on, data-driven neural networks when the machine learning topic. So it's a very, of course, appropriate topic. So please, let's extend a welcome to Chevalier Farhat.
Well, thank you, George, for this very generous and exaggerated introduction. It's really a pleasure. It's always a pleasure to come back to this country. It's a pleasure to come back to AUB and to share with you a little bit of what we're working on. So this work is the result of collaboration with many graduate students that the list is too long to be presented here, but a senior staff member is Radek Tezor, so I thought that I should mention him here. And it's really driven by the fact that I live in an ecosystem that is really driven by buzzwords. So it's buzzwords, and when it comes to funding, it's bandwagons. So we all heard about AI, artificial intelligence, about big data, about IoT, cyber physical systems, Industry 4.0, digital twins. And an engineer could legitimately ask, what is all this about? Well, clearly it's a Silicon Valley jargon, but at the center is machine learning for all these things. And it's what machine learning allows you to do, to dream of, and some other things that I will discuss, all in the concept of digital twins. So to set the context for digital twins, let me first start by defining what's a digital twin and give you some ideas of what is the concept behind it. So a digital twin, like you could expect from the word in English, is really a digital replica of a physical asset, but actually it doesn't have to be a physical asset. It could be a process, like a certification process. which means you're going to virtually certify something instead of exactly certify it. And its significance is that it's a virtual system, which means we're going to be talking about a software system that will allow you to assess the current state of a platform, how it's going to behave into the future, and enable you to do things that you have not been doing very efficiently before. For example, maintenance. Industry maintenance is a big cost. And then it will allow you to do an optimization of how you maintain a system, and I'll explain how. But first, let me tell you what is the origin of the words, where it come from. It came from a paper in 2011, so that's about 8 years ago, or at least this is how far as I could track it, by Eric Tugel and other people in Graphia in particular at Cornell. And the idea is that suppose, and that paper was written asking the question, suppose you have the following capability, what would you do with it? And before I tell you what to suppose, which is listed anywhere, I mean, it's really grandiose, it's probably ridiculous, but the question was not on how would you do it, the question is, if you had this capability, what would you do with it? If you had a capability that could take 1 trillion degrees of freedom, that was nonlinear, could handle ultra-realistic geometric details, could do multi-scale fluid structure, uncertainty quantification, everything you want. So essentially, you throw the kitchen sink at computational engineering, and you could do all this in real time. What would you do with that? And lots of things, and I'll show you what you would do with it. But very quickly, people started saying, well, how would I achieve this? And then the perceived enabler, and here I emphasize that at that time, is that it was conjectured that you'll be able to do it in some form of machine learning, software analytics, big data science essentially, that you would be able to do something with such a capability that is very useful to the physical asset or to the product that you're dealing with, as long as you could do it in real time. And by the way, this definition, I picked it up from Wikipedia. So if we fast forward to 2019, what has changed? Well, this is what has changed. No one is talking about trillion of degrees of freedom anymore. People are talking about quantities of interest, which means it could be a single degree of freedom that you're interested in. It should be one quantity that you have interested in. Could be a few of those. And then, when it came to machine learning, it was no longer like the perceived enabler. It was pretty much like the evangelized enabler, which means that, you know, if you believe in machine learning, it's going to solve everything, including every political crisis anywhere. So, GE, General Electric, has been a big champion of this. You could use it for assisting in the design of a physical asset. If you're talking about aircraft, you could optimize maintenance. How would you optimize maintenance? Well, if you build a digital replica, which is this computer model that is represented here by this digital replica of an aircraft, you could build a computational model. I mean, a finite element model, finite volume, finite difference, any model you like. It could be fluid, solid, fluid structure interaction, some model, electromagnetic, that replicates something of interest with this aircraft. And then usually models are imperfect. But if you flow data from the sensors, most aircraft, for example, are equipped with sensors. You send the sensors to the model, and if suddenly you can use the data that is coming from the sensors to improve the quality of the model, to get something where today what is the proper word is a data-informed model. It's a model that has been enhanced by the fact that you have data. Let's suppose that at some point your model starts predicting the next stream of data that is coming. So now you're happy with the quality of the model. And then it's really reproducing that data. So you can say that if it's reproducing that data, why do I still need this model? Because if at some point in time later it stops reproducing that data, well, the logic is the following. You don't question anymore the model because the model has been certified by now. Then you say something wrong has happened to the physical asset, so it's time to send the physical asset to maintenance, because if I cannot reproduce it anymore while I was able to reproduce it before, then something is wrong with it, so I'm going to maintain it. So that's an optimization of the maintenance process, because you're not going to do the maintenance based on some chart that says every X month you have to inspect a certain piece, whether actually the inspection is really due or not, but it's based on a specific event. Now, industry believes in this. Actually, before stopping here, I stopped in France, where I listened to a presentation from Valeo. And they really said that, you know, whether it's perfect or imperfect, whether it's going to occasionally give unsatisfactory results or not, we're not going to go backward, because the scales of the economics are such that preventive maintenance with digital twins is really what is everybody going with because of economics. Now, one thing I will argue today is that to trust a model, it does not really make sense to trust it in a deterministic way. You can only trust it in a stochastic way, in the sense that if I ask for an interval of confidence within 98%, which means that I have 98% probability that what I'm saying to you now really makes sense, is that what is happening to the system is somewhere at a given frequency, let's say, that it's responding somewhere between a lower part and an upper part. So I give you an interval. People call this an error bar, but it's really not an error bar. It's really how much fluctuation you can tolerate given that it's probabilistic. So this will make sense, and I'll explain to you why. Now, this is advocated for crisis management, for maintenance optimization of a physical asset, in order to be able to make an informed decision when you are in charge of that asset. And we will talk about these informed decisions towards the end. Now, about 6 months ago, last summer, ANSYS, who is a billion-dollar company and today one of the major software vendors, made a surprise announcement that ANSYS is teaming with SAP. How many of you have heard of ANSYS here? Great. How many of you have heard of SAP? All right. So those of you who have heard of SAP, you know that they have nothing to do with ANSYS. One does physics-based simulations, and the other, they do software for, you know, payrolls, for internet, for different things. And then I was curious, like, what got these two companies together? So what got them together is that they're announcing the first digital twin in their product, which would be able to really materialize the vision that I just talked to you about. And the example that is on their website, so I'm picking this from the website with all the reference here, seems to indicate, and I have to say seems, because I haven't used the product, but it seems to indicate that it is for the moment about quantities of interest, but probably it's more than quantities of interest, because what I'm looking at here is a flow in a tube, and then when I look at what we're monitoring here is temperature, head, speed, and flow, which presumably is at some point where probably there was a sensor, and then so therefore it's building something similar to what I've been talking about, and probably is doing even more than that. My point is that it's becoming a reality. A digital twin is becoming a reality. Now, lots of people would like to do it with quantities of interest because it's easier. It's easier because you focus on one quantity for which you have tons of data, because an engine on an aircraft typically has thousands of sensors that is on it, so you can pick at any point in space, you can have a whole history of what you're measuring. Usually it's temperature in time. And my point here is to say that the idea of focusing on a quantity of interest is not new. Engineers have always used response surfaces, which means that they measure or they compute, so it's a design of experiment type of thing, outputs that you can see here for some inputs that you see in blue, excuse me, yeah. And then if you ask by analysis what's going to happen at some point where you did not have data, then you do an interpolation in between. And then kriging came on top of this to be able to give you an error bar and to be able to give you an interval of confidence to tell you that actually it's not a deterministic value, but it's somewhere between this lower bound and this upper bound. And this is to represent the fact that if you want to do a response surface, which is a glorified word for an interpolation, is going to depend on the points that you pick. And therefore, there is an uncertainty that comes from the fact that you picked some points and not other points to draw your surface. So it takes this into account, among other things. And then there have been other attempts to do machine learning to be able to do classification and regression approaches to minimize the uncertainties and make these envelopes as thin as possible. And I was always curious, and I asked people, if I have a full aircraft, or I have a car, or I have a device, a computer, I mean anything, can I really represent its state with a quantity of interest, or 2 or 3? Can I really learn everything about it just by knowing what's happening at 2, 3 places? And the answer I was getting, well, you can tell me that it depends who I was talking to, but I was talking to the people around me, is that, well, anyway, who cares? All models are wrong, but some are useful. I have heard that thing since I was a graduate student. All models are wrong, but some are useful. So I decided to go and search it. And today you can go to Google and you Google it out. And I found that actually this was written by George Box in 1976, who was a statistician. I read the paper and I find it very interesting, particularly for all those who want to do machine learning of that type, you know. You download TensorFlow, you run it on anything that you have data on, and you see what you get. Yes, George Box did say that all models are wrong, but some are useful. But he also said, over-elaboration and over-parameterization is often the mark of mediocrity. And that is not as well quoted as the first one, because usually when it serves your purpose to say this, you don't want to say the other one, because then it will be hard to justify why you're making that curve more elaborate if George Box also says that that's a sign that you really don't understand what's going on. But that's what it is. Now, the point is that we're engineers, and that if quantities of interest is the best thing we can do, then by all means, that's what we should do. But there are many problems for which we don't even know what is the quantity of interest. And I thought I'll give you one, first because it's a cool movie. So this is the parachute for landing on Mars. That's, by the way, a program that was run under Charles Alashi at JPL, another great Lebanese. And you could see that every time that they tried in 2014, 2015 to make bigger parachutes than during the Viking programs, the parachute was crashing. And people became interested in knowing why it was crashing. Before it wasn't crashing, but it was smaller diameters. And now, obviously, we're making them bigger diameters because we want to land bigger payload on Mars. So JPL decided that probably we can build a computational tool to do this. A computational tool is pretty difficult to do this, but we can do it. This is what you see here. We can simulate, you know, the inflation, we can simulate the turbulence, and then we'll see in a second whether we get results that do anything besides colorful pictures. But I asked Lee Peterson, what is the quantity of interest now that we can really do Siri to look at? And the answer was, well, how do I know? If I knew what was the quantity of interest, I wouldn't need to build a model in the first place. So that's a little bit here, the setting is that if I don't know what is the quantity of interest, so okay, I mean, I'm measuring all this data on sensors. it tells me something about the engine, because if I see a data coming out of the engine that doesn't look like what it's supposed to do, this is fine. But it doesn't tell me necessarily about the whole state of the aircraft. Doesn't tell me what the aerodynamics is going to do, things like that. So, and by the way, for this thing, you can see here that the simulation can predict very well the peak force, 160, 158, and then the inflation time is pretty much the same. So the quality of the simulation is not the issue. The issue is that how can we learn what is the quantity of interest we should be looking at so that we can understand why the parachute was failing or not. Well, it's a good step that now we can simulate it. The next step is to figure out what is the good quantity of interest, if we want to do it this way. So when you think of quantity of interest, as I said, people think next machine learning. And then if you look at the definition of machine learning, it is essentially to learn from data without having a predetermined equation. And I insist on using the word equation, not model, because the whole purpose of machine learning is to build a model, but the model has to come from data. So essentially, it's not to build it based on an equation. And the idea is that the algorithm will have to improve when you start throwing at them more and more data. Now, machine learning has been developed by Hinton, that was mentioned, Jan LeCun, and many, many other people. I think Stanford today will argue that they have the center of gravity of machine learning. It made big impact when it started doing that image processing and trying to have, much more reliable classifications about images. But one thing you can say is that it succeeded at problems where one had lots of data, that's for sure, but one had based model. And actually the reason people were interested in machine learning, regression, classification, is because there were no partial differential equation that would help you solve the problem. If you are a banker and you want to decide whether you want to give me a loan or my colleague a loan, there is no partial differential equation that's going to help you decide whether I qualify for a loan or not. But if you start building data that says who in the past has failed in reimbursing the loan and who has succeeded based on, I don't know what, where you live, your income, your any kind of statistics, you could build a model that people could use to help you to make these decisions. The other thing is the notion of accuracy is not the same. If you're modeling a flow around an aircraft or a parachute, or you're modeling a mechanical system and you're trying to predict whether it's behaving the right way or not, it's deflecting a certain amount or not, it's vibrating at a certain frequency or not, we have some very precise concepts of accuracy. And usually, to add some humor, once you make the predictions, people will ask you, did you verify your results? Did you validate them? Do you get the same results as in experiment? And if you say yes, then say, then what's the point? We already have the experiment. And if you say no, then say, why would I believe you? So there is this culture. On the other hand, if you're trying to classify an image, what is the concept of accuracy? I mean, if you're trying to recognize a face, you either recognize a face or you don't recognize it. It's more like binary. It's more like a logistical rejection. You say yes or a no. So the culture is not the same. The metric of success is not the same. And on the other hand, if I have a complicated flow over a complicated aircraft, first, I will probably not have that much data in the first place. I'm talking here about physics data. I mean, if you're working on some particular experiment, you'll probably be lucky if in all your life you will be able to see a couple of pieces of data on that thing. And then the other thing, you probably have more models than there are people working on the problem. So it's not exactly the same situation as where machine learning has excelled. So the idea is here, I mean, how do you deal with this? Then there is another thing. Like many good things, things get exaggerated a little bit. So let me tell you this, what happened about a year ago. So NPS, which is a famous conference for machine learning and artificial intelligence, NIPS had an award that's called the Test of Time award, and the person who, or the team that wins this award has to give a presentation. And it's called Test of Time because it's about something that you published 10 years earlier, let's say, and it's still pretty powerful. And then Ali Rahimi, who is at Google, won the award last time, and for a paper that he wrote with Ben Recht called Random Features for Large-Scale Kernel Machines, and that was in 2007, 10 years earlier. Actually, I like that concept very well, to measure the impact of a paper by going to 10 years earlier to see how it was and what it's doing today to the landscape. And at a time where my colleague at Stanford, Andrew Ng, was promising that AI is going to be the new electricity, which means that it's going to be fueling almost anything, Ali Rahimi, who won the award and stood in front of everybody, said machine learning has become alchemy, meaning that it was supposed to be a science, and now it has become alchemy because people are using it without understanding why it works, why it should work in the first place, and almost trusting anything that comes out of it. And I find it interesting that in a community where we used to use vocabulary like optimization, like solving an inverse problem, like identifying coefficients, now all these words have been replaced by we're learning this, we're learning that. So that's why my first slide was about buzzwords and bandwagons. Now, this is not to say that machine learning has not solved real problems. It did. There's no question. This is to say that you can't just take it because it's a hot bandwagon and apply it blindly to things without understanding what it does, particularly when you are in a situation that is not exactly the situation that it has been developed for. And let me give you an idea. This is something I ask all my students, so I'm not going to insult your intelligence, but since I ask all my students, I'm going to tell you what I ask them. If I have a function R of a parameter mu, and I have two parameters, two values, mu1 and mu2, and I know their values, R of mu1 and R of mu2, and if I say, I'm interested in knowing how would you estimate R for a variable value mu3, somewhere between mu1 and mu2, and if I ask Professor Turkiye, what would you predict? Well, probably he's going to tell me, well, that's a trick question or what? Then I'll clarify that it's not a trick question. You say, okay, well, in that case, I'll just do a linear regression. I have only 2 points, and it's somewhere here. And that's fair. That's all what we know, unless you want to add some kriging on it, some probabilistic thing. But what if later I tell him, nothing has changed, but I got a phone call, and somebody told me that actually there is one particular circle of interest that goes through these 2 points. And I'm saying in one particular circle because there is an infinity of circles that go through these 2 points. But there is one that was observed that actually these 2 points belong to that circle. Would you guys like to, and ladies, to revise your estimation? And the answers say, this is actually a trick question. So it's going to be probably either the point on top or the point below, but not the point on the straight line, because now I got new information that is the circle. And the question becomes, well, is it the point on the top or the point that is below? And actually, that's the wrong question. The right question is, who is going to tell me that there is a circle that goes through these 2 points, a particular circle of interest? Where is going to get this information? And that's the difference between data and information. We can talk about big data, but it can have little information, or I can have little data and it can have big information in it. And of course, for those who can appreciate the difference, you can say that's semantic, but to me it's a little bit more than semantic. So if I had lots of data, by the way, I would have discovered that actually it's the upper circle or the lower part of the circle, because there will be many other data points, and I could do my regression on it. So that's the problem that happens when you have limited amount of data. And when it comes to do physical experiments with engineering, we always have limited amount of data. If we're doing image processing, we have tons of data. If we're getting image from satellites, we got tons of them. But if you are doing experiments on a car, if you're crashing a car just to be able to learn something about the safety, and I'm doing the same thing here, I'm using the word learn, you're not going to crash 1 million cars just to be able to make sure that you can do a regression with more points. So maybe there is a better way to do it. And here is the better way. Let me show you an example. So this is a simple fluid structure interaction problem where you can see the wing. The wing has a fuel tank. There is fuel inside because you need to put the fuel somewhere. And then it's vibrating because there is an external flow. So there is an external flow interacting with the structure, interacting with the internal flow. And we were able to demonstrate that we can compute the flutter speed index, which is at which speed of the aircraft some instability can happen, so to be able to prevent it from happening. We can do it in real time using a process called model reduction that I explained later. And to demonstrate that you could do it in real time, we put it on an iPhone. So, but here's the idea. This is the experimental data that comes from experiments, let's say. And you can see that this is the flutter speed index. It doesn't matter for the purpose of this discussion what physically it means. It is my quantity of interest, if you want, and depends on two parameters: the speed at which the aircraft is going and how much fuel is inside the aircraft. And I extracted from this data, I extracted this database. And I put these two circles on purpose to show you that I stopped the database at this point here, which means I know nothing about this other behavior that you see of the curve here. And in this area here, I truncated here, so I pick a point here, a point there, which is a point here, a point there, and therefore I know little about this information. And then what would happen if I do regression on this, which is like the basic step of machine learning? So if I do try to reconstruct now this surface from this database with a simple regression, which is the element, and it's cubic, you could see that it will be able to fit a cubic here, so it'll be able to do an approximation of what you see here, but there is no way it can predict what's going to happen behind it because the database has no information in it. You won't see it. On the other hand, this is a linear interpolation, not a cubic, but on a manifold, which means I have used a model that to be able to, a physics-based model, to represent what this physics behavior is, and I have trained this model only on these few data points, and you can see that when I do this, the model gets a much better representation of this dip here, but more importantly, I can now get a regression that can capture the correct behavior here, even though there is no data, because I am learning not only from data, I'm learning also from models and not from data points, which means that we need to have models in the first place and not rely on the data to build the models, but perhaps rely on the data to enhance a model that we have in. And that's, in my opinion, one of the ways. It's very hard in science to say the only way, but that's one of the ways to be able to deal with rare data, with few data, and not with tons of data. And not every problem has tons of data. So this will set a different vision for digital twins. So we're not going to focus on a quantity of interest and simply on running a machine learning, standard machine learning algorithm. What we're going to do is first to do a special type of model reduction called projection-based model reduction. And this is going to give us the speed. And then we're going to admit that no model that we ever do will be perfect. And therefore, we're going to see how we can use data to enhance this model. And that's what I call the probabilistic modeling of ignorance. I mean, if there are things that I don't know how to model, well, That's the truth. I don't know how to model. So how can I get data to help me model it, but not model the whole thing, only the part that I don't know how to do well? And this will give me a digital twin that will work in real time. I'm going to show you numerical data, and at the end of my talk, if you're still awake, I'm going to show you a robot that is really operating under these things. So where is machine learning with all this? Well, machine learning is going to be used as a technique to be able to achieve each one of these objectives, but not as the standard technique on the whole thing applied to a quantity of interest. And this brings me to the first step. I will simplify it as much as it makes sense for a global audience like this, is to summarize in one slide what is projection-based model reduction and why it is the oldest form of machine learning. As you know, machine learning has a few steps. It has a step that is called a hypothesis, then you have a representation, then you have to formulate a loss function, and then you have to solve an optimization problem to minimize that loss function, and this is how you get, your regression, or you can get a classification. So here, we're starting not from data, we're starting from model. So my model is some partial differential equation R of u and mu equals 0, where mu is the parameters. It's the design parameter. If I'm designing a car, is how I design. I vary the parameters, and I do these things. And the first thing I want to do is to say that I would like to solve this problem, but I would like to solve it pretty fast. So I'm going to make a hypothesis. And the hypothesis is that I can assume that the solution of this problem is affine, which means that it's in a low-dimensional space. It's almost locally as a straight line. And by the way, a neural network used to use sigmoid functions to do a similar assumption, but now has been, in order to increase its speed, go into functions that look exactly like this. Second, we're going to have a representation, which means we're going to say that this solution can be represented by a few modes. So if you remember Fourier modes, if you remember, eigen decomposition, that's for linear problem. That's a generalization for nonlinear, where can you have a few modes. Where am I going to get these modes? I'm going to get them from a design of experiments, which what every engineer used to do before the word machine learning was very popular. So we're going to do some design experiments to learn this V. And then I have an approximate solution that is some reference plus V delta Y, where delta Y are the generalized coordinates. And how will I get my generalized coordinates? Well, I'll formulate a loss function, which is that if I take this approximate solution and put it in my model, it has to satisfy the governing equation. So I call this a residual. It has to satisfy that the residual is 0, which means I have to solve an optimization problem, which is to minimize the norm of this residual in order to get delta Y. So you can see that this type of model reduction has every element of machine learning. And towards the end, I'll show you how probabilistic reasoning is injected into it. But let's see how it's done in a practice. So you're interested in designing something like this car that you see here. And then you take your favorite modeling and simulation tool. And then you do a first simulation for a given design that is represented here by mu1. This is a trajectory, and then you sample this trajectory, which means at every point here, it's at some point in time, and every triangle is like whatever number of degrees of freedom this model has. If it has 1 billion degrees of freedom, every one of this triangle has 1 billion. It has the whole state of the solution at a particular time. And then you say, what if I change the design? I change the parameter mu1, I get a parameter mu2. So I get a totally different trajectory of the state. So I'm really doing a design of experiment. What if I change this, I get this, and I sample it again. And what if, and I sample it again. And now you can see where I'm going with this. And now what if I forget where this data came from? I forget that I even used simulations to get it. And now I have this data. So now I am in the big data scenario because I have used a model to generate this data that it didn't have. It is a synthetic model, however. It's not an experimental model. It's a synthetic model. And now I say, what if I want to compress this data to build a smaller model, a little bit a la machine learning, that will be able to reproduce this data for any value of the parameter mu. So the first thing you observe here is that in this area, you have a circle, you have a triangle, and you have a square, which means that for that car, no matter how you change locally some of the shape of that car, the system was responding in the same way, but not necessarily at the same time, which means that there are some behaviors of the solution that are invariant, but they come later in time or before time, so we get into the problem of classification. So we can run a classification algorithm, and this classification algorithm will detect that there are 5 pieces, or 1, 2, 3, 4 pieces, 4 regions, where the data has a different behavior. And then we have the center of gravity of all these data. We can compress these data, and when I compress them, now I have a basis in each one of them, and I have a representation. And therefore, if now I come and I go online and I ask, what would happen if I change the car and get this different design? And therefore, I am going to try to get an answer by simulation for an untrained value of mu star. Then, when I'm trying to integrate the system, if I am at some point, I have to measure the distance to any one of these subspaces that you can see here. And if I find that I'm the closest to this region, I will try to use a reduced order model that comes from this data, which means a data-driven model from this region of the data in order to approximate the system. And later on, the system will find that actually now I'm closer to this one, and I use a data-driven model coming from this data to approximate this system. And this is how I can approximate a nonlinear, highly nonlinear system throughout this. So this is one approach to do this, but now we have to settle other questions. The first question is, this is great, but how will I pick my points for my design of experiments? How will I address this? And the other one is that, how much data do I need? If you are in computation and you have been working with partial differential equations, you have space and you have time. And we have the concept of convergence. If I refine the mesh enough, hopefully I will converge. If I refine the time step enough, hopefully I'll converge in time. But when you come to learning with data, how would you measure convergence? How would you know that you have enough data to be able to train a model? When is enough enough? That's a separate issue. So this is one way to show you how this is done. So this is how you do it. Suppose you have a 2-parameter space. I start by building a reduced order model offline at one point. And then I go and I do a loop where randomly at each step I consider a bunch of other points inside the parameter space. And I try to use this reduced order model to replicate the solution at any one of these points. And then obviously I'm going to fail because this point is trained only in its neighborhood, so its trust region does not cover all these points. And what I'm interested in is the points here which the error of the prediction using this point is the largest, because this means that I don't have much information about what's happening there. So if I identify that this is the point where the error is largest, I'll go and retrain my model at this point, which means I need data that comes from this point, and I keep doing this until I have enough points, and that tells me exactly which values of mu and how many data points do I need to train it. So let me show you some example on a real aircraft. So here is an aircraft. This is the Boeing 777. This one is still flying very well. And this is the common research model that is a surrogate model of this that is published by NASA that can be downloaded from any website. And this is a simulation of cruise condition at Mach number 0.85. So this is in the transonic regime. There are shocks. It is nonlinear. There is a turbulence model, the Spalar Almaraz. And then there is a four-dimensional parameter space that has to do with the design of the aircraft. You have the wingspan, the vertical wingtip rate, the streamwise wingtip rate, and the outboard twist rate. What we're interested in is in what-if scenarios, and that's the first steps towards shape optimization. So what we're interested in to ask something, the question like this. This is the aircraft. What would happen if I had made the wings a little bit longer? And then you do the simulation and you say, well, you will get 10-point drags more. Is this really what you want? Well, that doesn't sound like a good idea. So we train the model like this. We ask questions like, what if I did this to the wing? Then we get the answer. What if I twisted it? We get the answer, etc. This is the twist. And then in order to speed up calculations, we found ways that where we don't need to compute on all the grid points, but only on selective grid points. So that's machine learning locally used to find out where are the quadrature points that really need to participate in the calculation. And at the end of the day, in 2 hours on 24,000 cores, so you need a big machine, we have built a reduced order model that is ready to go online. So you come online and you say, what if I change something in the design here? You see, I want to go to do it this way. Think of this as being an optimization loop. Then, in less than 3 minutes, you have the answer. You have the answer of a simulation that used to take 2 hours on 24,000 cores. Now it takes 3 minutes on a laptop. And that laptop was a thin air MacBook. You can get it that fast because that's the machine learning. You have trained the model ahead of time, offline, and then now you can come and you can operate in real time. Let's not lose from the fact that we want to do a digital twin with it, but at least now we have a capability of modeling that can operate in real time. By the way, how accurate it is, so I'm going to look at cross sections here of the wing at 15 meter, 20 meter, 25 meter, 27 meter. If you are an aerospace engineer or a mechanical engineer, you're probably familiar with this. I'm going to look at the pressure coefficients across the chord of the cut that I made. You can see in blue the high-dimensional model, the one that has, millions of degrees of freedom. And you can see in the red my reduced order model that runs in real time. And as far as I'm concerned, they give virtually the same results. Now, in practice, we're not going to every time go and do the high-dimensional simulation to check that what we have is right. That's what the greedy procedure gave us, the convergence of how many points in the design of experiments we need. So that's the results that we would expect. So this works well, but now when we correlate with flight test data, not high-dimensional numerical model data, we may see that actually the solution we have doesn't match the experiment very well. And this is where you can blame a number of things. So there have been two trends, one that is epsilon-esque and one that is 99% of the literature. And I always thought it was more fun to argue for the 1% than for the 99%, because if you get it right, then someone's going to remember it. But if you get it right among the 99%, well, there are 99 people who are doing it. Deal. The idea is that if you're not obtaining the same thing as is in the experiment, your material properties that you put into the simulation probably were not perfect. Whatever people told you that the Young modulus is this, or the aircraft was flying at this speed, in reality, this was not the correct data. So this is uncertainties on the parameters. I really don't think that that's really what happens in many cases. Probably it happens in a few cases. I don't think that it's what happens in many cases, because if you're building an aircraft and you can't trust what your supplier, or building a car for that matter, and you can't trust the data that your suppliers give you, you change the supplier. I mean, you don't start doing uncertainty on that thing. I think what's the biggest thing is the following. This is a real aircraft. And whether you are expert in this field or not, just follow here the intellectual discussion. If you want to build a mathematical model for this aircraft, I mean, look at how many pieces this aircraft has. Look at how many rivets it has, at how many bolts and nuts it had. You're not going to model every one of them. At some point, you're going to make decisions that are modeling decisions to say, I'm going to account for this, I'm not going to account for that. You're going to assume that this is negligible. You're going to make assumptions because we're human beings to be able to build a model that looks like that. This is a structural model in that case. Well, the uncertainties are going to be primarily coming from that decision that you make of what to include and what to exclude, a mass that is supposed to be distributed that you decided to lump it at some places, a friction that was happening at some point that you have no idea what's the friction coefficient that you're going to ignore it. There are going to be decisions like this that you're going to make, and these are model form uncertainties that you're going not to allow for. And therefore, plus, if I do a model reduction that I talked about, or a machine learning, it means I threw away all my high-dimensional model and I'm replacing it now by something that I learned. So that's throwing more uncertainty into the process. Was the learning perfect? So in order to deal with this, people have been doing this, as I told you. They said, let's randomize the parameters. I am not sure what was the coefficients of the material property. Let's assume that it's random, and then you have an uncertainty in the input, and the whole research has been about propagating the uncertainty in the model to get its effect on the output. If the system is linear, that's a simple sensitivity analysis. You get the uncertainty on the output as a function of the uncertainty on the input. If it's nonlinear, you have to propagate it, and tons of research has been done there. Well, if you're confident that it's all about a variation of the parameters, you can do this. But I really think that a lot of these uncertainties come from these decisions that I told you about, that we're making decisions about what to put in the model, what not to put in the models, on which we don't have control. There's another reason why I don't like this approach. Let's suppose that here is your experimental data. And let's suppose that deterministically, you go in a deterministic sense, and you keep changing P. You keep changing the parameter in a deterministic sense. You get a family of solutions, and none of them capture the experimental data. So now you come and you randomize the P. All what you're going to get is exactly that same envelope and one additional information, which is what is the probability that the answer is this instead of this, instead of this, instead of this, instead of that. But it's not going to give you any means to go and recover that. So it's not going to help me improve the model, and therefore I won't be able to reach what I call the state of a data-informed model. So what can we do instead? So this is what recently, only a couple of years ago, we proposed, is that I don't want to randomize the parameters. I want to randomize the subspace in which I'm looking for my solution, which means I want to randomize the method that I'm using to find the solution. So that if one method does it, so I'm going to look for a family of methods instead of a family of parameters, hoping that one of them will capture this. And there is a reason for this. If I believe that my model is imperfect, well, changing the parameter is not going to make it any less imperfect. But if I'm changing the method by which I'm solving the problem, is you go back to a classical tool of modeling called the manufactured solution. It's like I'm building a model for which that method is perfect, and therefore I am varying the models until I match the solution. And that's how I'm going to get a model-informed data. So essentially, I'm going to look at the basis where I'm looking for the solution, and instead of using a deterministic basis, I will use a probabilistic basis. So when it's heavy character like this, it means that it is probabilistic. When it's a light thing like this, it means that it's deterministic. So if I randomize my basis, now I have to make sure that when this basis is randomized, it remains a basis, which means that all the linear columns, all the columns of that matrix that contains the basis have to remain linearly independent. So I have to randomize this basis under this constraint. And that's something that is difficult to do in machine learning, is to learn under a constraint. If you want to learn something about a mass distribution, there must be a constraint that says the mass is going to remain positive. If you're going to learn something about temperature, how would you guarantee that you're still satisfying the second principle of thermodynamics? If you want to learn something about dynamics, how are you going to guarantee in that regression curve that you're satisfying the principle of action and reaction? How are you going to guarantee that you're satisfying the second Newton principle? When you're doing a face recognition, you don't ask yourself these questions. At the end of the day, do you recognize that face or don't you recognize it? So that's an element here that we have to do this. And without getting into mathematics, there is a procedure that we built to do this, but here's the answer. Is that if this is the manifold of the solution, and that's the last slide of mathematics, hopefully, it simply tells you that my deterministic solution, I'm adding something to it to give me my probabilistic basis, which means that when I build my information around this data, I am going to look not only of what happens here, but what happens in the neighborhood so that I can extend the scope of my solution to go and get that data. So I can build a reduced basis that depends on a set of hyperparameters. And now if I give them some values, they will change the basis, which means they will change the solution method, which means they'll change the model, and then they'll give me a different answer. So the question is, how will I determine alpha? Well, this is where another form of machine learning comes with, is that I set another regression that all this math is to say something that's very simple. It says that now that I have a probabilistic basis, I have a probabilistic model, which means that when I run my model, I'm going to get statistics. I'm not going to get a finite, answer. I'm going to get the probability that my answer is between something and something. I have stochasticity here, but my data is either fixed or it is stochastic. It doesn't matter. If it's fixed, then its mean value is itself. If it's stochastic, it has its own stochasticity. It has a mean value, it has a standard deviation. And I'm going to formulate an optimization problem that says that I want that the data generated by my model have the same statistics as the statistics data that I have measured. And that for any quantity of interest, because you're going to measure at some quantities, but that's infused in the model. So I solve this optimization problem, which is stochastic optimization problem. That will give me the alpha. Once I have the alpha, I put it into the V, so I put it into my model. So what I have managed to do is a mathematical framework that can use data that comes from experiment, extract it, extract the information that comes with it, not only the data in the form of the statistics, the moments, and then infuse it inside the model via the reduced basis V. So let me show you some applications here and see now concrete examples. So we built this little aircraft. We worked with a team at the University of Minnesota to build this aircraft. And when we build this aircraft, that's a toy aircraft that flies. That's what students do. We asked two teams, we gave them funny names, Cole and Hattie, to go and measure the vibration frequencies of this aircraft. And in order to make sure we're going to get reliable data, we asked each team for each mode to use two different identification methods and give us the data. So it was interesting because the first team for the first frequency got about 10% difference between them. 10%, that's quite a bit of a difference for identifying a system, because if you want to build a controller, 10% makes really a difference. On the other hand, there was no variation between the two different methods, only a variation between the two different teams. Then we go to the second mode. The first team was able to get the answer. The second team was not able to get any answer. They couldn't identify it. Now this replicates for you what may happen with your sensor. One sensor turned out to be faulty, the other sensor was working. Assume that these people were sensors. Then here it was the opposite. The first team could not identify anything. The second team, using the second method, was able to identify this frequency. Here they both identified more or less the same thing. Here none of them was able to identify anything. And then here the difference is about 20 to 25%. I mean, which one would you believe? That's what's going to happen with data. And then the question is, when this is the quality of the data that you have, how do you use it to inform a model, given that the data itself doesn't agree? So we built a finite element model. This is clearly not a stick model, but we assumed it is a stick model. The mass is usually distributed. We assume it's a lump mass. It's built of composite. We assume it's homogenized composite. There is usually some damping. We assume that is undamping, which means we did all these errors. And we computed our own frequencies. But that's at the deterministic level. And then we ran the stochastic thing that I showed you, that how we can learn from data to trace the model. So in this graph, I have the eigenfrequencies as a function of the rank, which means mode 1, mode 2, mode 3, etc. And look at it. This is the two data points. In black is all the experimental data. So they don't agree here. Here I had only one. Here I had only one. Here two that are very far apart. This is my deterministic reduced order model. It was pretty close here. It was far here, very far here. Here, anyway, I don't have any other data to compare to. Here it was close to one of them, but not to the other. And then here is my statistical reduced order model that run in real time. And you can notice that it always brackets the experimental data. It always brackets them. Here I don't have experiments, so it tells you it brackets the deterministic one. Here it's bracketing both data points. So it does give me the right interval of confidence of where I should expect my solution to be. This is in another example for a MEMS in this case. So it has a mobile part, it has a suspended part. It's a complicated model that has all kind of rotation. It was done with Christian Suarez. And then what you can see here is that the experimental data is in red, the deterministic data is in blue. And then and you can see that the blue sometimes really is out of line with the red. It's not doing the correct prediction. But then if I go to my stochastic, in real time, within 98% confidence, it's predicting that it's somewhere between and here. So it always brackets the red, occasionally on the boundary, but most of the time it brackets it deep inside. So it's within the same thing. So let me conclude this by something that was similar, but do a conclusion here with three parts. So this is really what we can do for digital twins. So you can see they are feasible. We can learn from data to enhance our model. We can do it in real time. But they are still in its infancy. So I would like to know how ANSYS is doing it to see what's the relation. But you probably all have Intel computers. And then you always, seen this logo, Intel Inside. And I don't know if, like me, you ask yourself, what does it mean? Anyone figured out what it means to say Intel Inside? What? They may Intel. Maybe. I think it's because they think that there's an idiot that is outside. And so for the next generation of aircraft, we're not going to have idiots outside. We're going to have a digital twin that is inside that's going to help this aircraft do as good a job as possible. So let me show you something that comes close to this that is done by my colleague Marco Pavone. So this is a fencer that is fencing against a robot where there is a digital twin inside that is doing the control in that case. And then look at it. It's learning pretty well. Now it learns something else. You're going to see what it's learning. So now there is a net, and it's having fun here. And then the fencer is going to come this way. And you're going to see the result of the training. So it's still the same thing. It senses the danger. It gets away. And at some point, it tells the fencer, you know what, I'm really tired of this. So you get out, and it's smart enough to get around the net and say bye-bye. So that's what you should expect for the next generation. The real conclusion at the end is that this is my experience. Some students were asking me, how is the job market for computational modeling? It's pretty high. It's pretty high, and it's actually in tiers. There are those who are doing modeling and simulation for prediction, trying to understand the physics, trying to understand how a system is going to react. These are usually the people like you and me who are really interested in science and advancing this and being predictive. But the people who are calling the shots, they are the people who want a different kind of modeling and simulation. It's the modeling and simulation that will tell them whether to go ahead with the project or not go ahead with the project, to invest into something or not invest into something, to make that acquisition or make that other acquisition. These are the people who run the show. They could tell you whether you hire this faculty or you hire this other faculty. And they need something in between that operates in real time because they have a very small tolerance for lengthy simulations. And the model and simulation for prediction is physics-based. We all know it. This one is based on data analytics, but you can't do it on data analytics that is not informed by something that is relevant. So what really the digital twins, it's filled the niche of the middle layer that is going to do something that is based on a probabilistic model reduction, that be able to fill the gap between the two so that you can make both communities at the low level and the high level very happy. Thank you. Everybody needs to hear you.
Okay. I just want to ask about the last bit. So you said you have a physical model, and you suggested or you proposed the idea of doing stochasticity or randomization on the model itself.
Yes.
Let's take, for example, just for the sake of, let's take the Navier-Stokes equation.
Yes.
So you solve the problem, and then you do reduced order, and then you introduce the stochasticity at the level of the reduced order while satisfying the governing equations?
Yes, exactly.
How would you impose the governing equations on the randomized model?
When you go and you say, I'm going to look for a solution in a specific subspace, which means you're using some global shape functions to say the solution is a combination of these global functions. You agree? Your shape functions have been determined from the design of experiments. They have been determined from a learning process. But the coefficients of combining these modes are unknown yet. When you take that combination and you say it has to solve my Navier-Stokes equation, it will give you a system of equations in these generalized coordinates. If you put only 3 modes, you're going to get only 3 coefficients, even if your Navier-Stokes equation had 100 million degrees of freedom originally. You follow me up to here?
Yes, yes, I know.
So where stochasticity comes is that why am I going to decide that there are these 3 particular modes? Why don't I think about these 3 particular modes, if 3 happen to be what you care about? Why don't I think of them as being the mean values of some random modes? But they are random, but with this mean value, which means they have a probability model that is represented by this mean value and some other features. And then you parameterize this probability model by a hyperparameter alpha, and then you formulate an optimization problem that says, every time I change alpha, these mode shapes change. And once I have these mode shapes, I can compute the generalized coordinates, so I have an approximate for my Navier-Stokes equation. But let me go back to these alpha. How am I going to determine them? Well, let's be happy first to say that if I give you alpha, if I call somebody and they give me alpha, you agree with me that for this alpha, you'll get V, and you'll solve the inverse problem, and you get the Y. But how am I going to get those alpha? Well, I'm going to say, since for any given alpha, I know I can compute a stochastic solution, then I'm going to set up an optimization problem that says, give me the alpha that will make that the stochasticity of my model, of my analytical model, will reproduce the stochasticity of the data that I'm having, and will reproduce it for whatever quantity of interest that I have. I've never used a limitation of myself to the quantity of interest, but I learned from the quantity of interest. And therefore, the model was for the entire system, but it was optimized for the quantity of interest. And I'm arguing that this is far better than having to bet on a quantity of interest. Here, I'm only betting the training, but not the modeling.
Thank you.
Hi. I think you answered part of the question, but I'll ask it anyway. So while you're learning the model, what would be the advantage of putting or actually learning the model itself versus changing the model and learning the parameters of that model? I suppose the solution space is very large and you can't do that. Is that correct?
I'll give you an answer, but before I give it to you, I'll ask you to allow me to give me some freedom of how I'm going to answer it. If you learn the parameters, and I always find myself funny when I use the word learn I mean, you're going to solve an inverse problem, they're going to give you the optimal parameters. You agree? What if I go to the lab now and I measure those parameters again? And they are not what the inverse problem is telling me. So who would you believe? Would you believe those numbers? I was trained by the Jesuits, so now I answered your question by asking you a question. Would you believe this? Well, so that's why I don't believe in that. On the other hand, so I call this, there is a cup, and the cup is telling you can't do that because you just are telling me that by solving your optimization problem, you're getting material parameters that I go to the lab, I remeasure them again, and I remeasure them again, and I get 3 other people to measure them again, and they don't match what my learning model is telling me. So what's the point? On the other hand, if I learn the model, I'm changing the model, which cop is going to come and tell you this is not the right model? You can do whatever you want. It's your model. You're proposing that. There is nothing that you can go to contradict that when you have done it in such a way that you're respecting all the physics because you're feeding back that information into the assumed physics at the beginning of the Navier-Stokes equation, let's say, where you're satisfying momentum, you're satisfying mass conservation, you're satisfying second thermodynamics, you're satisfying all these things in a least square sense, but you're satisfying them. So you're preserving all the constraints. While when you're modeled with just a data or a parameter, you have no idea what you're satisfying, what you're not satisfying. That's the rationale.
But now I'm going to ask my question in the same way in the paper you mentioned. Suppose that you have a model reduction method for nonlinear systems, which is able to give you, like it is input independent, and it's able to give you an error bound on the reduction error. So how would you use that in your framework to improve it?
But that's exactly what we're using. Let me remind you of what is happening here. You remember this design of experiment? Every time I started with this blue point, every time I throw in more data at it, I'm relearning the model. and I go and I randomly pick a bunch of other model in the parameter space, and I check whether the improved model is producing the same answer at any point in the parameter space. And at the point where it's not doing well, I take that point, that's what I do here, I take that point and I retrain again it here. And I keep doing this. So at some point, when I look at the point where the error is maximum, if I already find that the error is below a certain threshold, it means that my model has learned all the data points that are in the space. All within the probability measure that is used here. No, it's only inefficient when you have something better. And I have used here this to just explain it to you, and your comment is true. As is like this, it doesn't scale very well. So I can tell you this, for a much higher dimensional parameter space, and that's a very good question, first thing we do is we do a data reduction, which means we only scan the dimensions of the data that are the most active with respect to the solution. It's an approach known as active subspaces that goes and pick only the data to which you're sensitive. So there are ways, there is clustering that you can break it into pieces. There's no question it becomes more intricate, and when at the end you still cannot do it, it's an open research topic. What is important here is that there are schemes that are without feedback, that are non-adaptive, which means they sample the parameter space on what you want to go and learn before you even test your model. This approach is called greedy because actually it has a feedback. It is adaptive. The next point I'm going to learn depends on how well am I performing now into that parameter space. And I find the region where I'm not performing well and I go and I train there. Yes, being a greedy, it will suffer from the curse of dimensionality. So again, I was focusing on the main approach. There are approaches to deal with the curse of dimensionality, and eventually, if you have a very, very large parameter space, it is a open research problem. So I would just conclude this question by saying, if you noticed, when I did this aircraft, it has only a 4-dimensional parameter space. And partially, I'm not hiding it, is to address exactly the question. Because when we did it, we did not have a technique to go address this. Today, we do better. Next year, we'll do again better. So it is an open search topic about how you do it for higher dimensional parameter spaces. But again, I was honest when I said I wouldn't call this inefficient because it is inefficient if you know how to do it better than this. And for the moment, I don't think anyone knows how to do it better. And by the way, that will be the same thing if you're doing a neural network. You have to train the neural network with data. With data, where are you going to sample that data? Right now, the neural networks have been built for data that exist. Here, it's a slightly, not a huge more, but slightly more complex problem that I have to decide which data I'm going to generate and then build, if you want, a neural network on top of it. But most neural networks have been built for data that exists. You assume that you have a data, you have tons of data, you run it on them. We're not in this situation. We're trying to generate the data that we want so that we can build a model that we want.